All right, our last set of notes on the pendulum deals with the energy transformations after you let the pendulum go. So you pull the pendulum bob to the side and you've given it potential energy, and then you let it go. And down here at the equilibrium line, the position, it's going to have some kinetic energy after it's fallen from a height h down to what I've called the floor. Now, the floor doesn't actually have to be the floor. It's the floor for the motion, that's why I put it in quotes, the floor for the motion of the pendulum bob. The pendulum bob is not going to go any lower than this because it can't. It's held up by the string, and the string is not going to break. If it does, then the pendulum bob turns into a projectile. We're not going to deal with that right now. We're just going to deal with the pendulum going back and forth and the potential energy on this side turning into kinetic energy and turning back into potential energy indefinitely. No friction, no air resistance, just potential energy turning into kinetic energy. Now I've drawn, say, the right triangle here. The the adjacent side of the triangle is L cosine theta, and the hypotenuse is the length of the string. But the length of the string is not going to change. So the length of the string when it's pulled to the side is going to be the same as when it's straight up and down, which is where this height h comes in. The height h is just going to be the difference between the total length of the string and the length of that side of the triangle. So the total energy is going to stay constant because we have no air resistance and no friction. So total energy at the beginning, the original, and the final, these guys are the same. And the original, once again, we're going to start with it at maximum amplitude, not moving. And we're going to let it go, and it's going to move back towards equilibrium, where it's going to end up with all kinetic energy. So this is going to be max potential, and it's going to shift into max kinetic. Maximum potential energy for an object near the Earth's surface, so the weight isn't going to be changing much. We don't have to worry about what we did in the last chapter with gravitation. And on the other side, we're going to have 1/2 mv squared. So if you take a look here, this h, I want to get rid of that h. Let's get rid of this h and put it in terms of L and L cosine theta. And it's going to be the difference between those two guys. So h equals L minus L cosine theta equals, and we can factor out the L to put it in one spot, and then we have 1 minus cosine theta. And then when you plug in any particular theta, you can get more specific for what this expression is. Let's see here. So let's get rid of the mass, because we're dealing with, again, in a simple pendulum, all of the mass is in the bob, and it's so much heavier than the string that we can basically just ignore the mass of the string. So we're going to have G, and instead of H, now we're going to have L, and our expression from that triangle, 1/2, and this velocity over here, as long as this is maximum theta, this is going to be maximum speed. Don't forget to square it. Rearranging, solving for the speed, I'm going to have a 2, G, and L, and then the fact that it's a pendulum. Which this expression should look fairly familiar. Fairly familiar. Suppose we pull the pendulum bob all the way up so that it's at 90 degrees. Well, cosine of 90 is 0. 1 minus 0 is just 1. And what we've effectively done is lift this pendulum bob up to here, a height L, let it go, and how fast is it going when it gets to the bottom? Well, we're going to have 2GL. This expression right here should be very familiar from way back in kinematics when we discussed this back in September. So this is our quick and dirty check for, did I make a brain fart? No, I didn't make any stupid mistakes. I have 2GL as expected, and then I'm going to modify it by the fact that I'm not pulling it all the way up. I'm just going to pull it part way up with this pendulum to let it swing back and forth. All right, and that concludes. Okay, now we've discussed energy. That concludes our notes on the pendulum. We have the relationship between angular acceleration and angular displacement. And again, this omega here is 2 pi over the period. And then we use this and torque to come up with an expression that is usable to describe the period of motion of the pendulum bob. And you notice how the mass of the pendulum bob does not matter here. What matters is how long is the string and what planet are we on. This is a very similar expression to the one that we had for mass on a spring, where we had a 2 pi, we had a square root, and then it depended on how heavy was the mass and how stiff was the spring. This, being a slightly different contraption, is going to have different variable relationships over here. Now, taking a look at energy considerations, we have potential energy turning into kinetic energy and back again. And we can see the relationship between how far to the side did we pull this guy, so how high up is it starting out, and then how fast is it going at the bottom of the swing. And we can see that the higher up you pull it, the faster it's going to be going at the bottom of the swing.